Here, let's dive into Maya's node connections and take a look at how the parent constraint actually works inside Maya. As for how to open this window and how to connect these nodes, we don't need to worry about that for now. We'll go over all that in detail in a later chapter. For now, let's just focus on the relationship between their attribute connections. There are a couple of things we should know beforehand. First is our node itself. Here we see two columns, left and right. We need to remember, the left side is for our input attributes. All the values come in from the left, and then some complex calculations happen inside our node. Then the result is sent out from our right side, the output. Another thing is the state of this connection. We have a circle on the left connecting to an attribute on the right. It also has an arrow. This just means the value of our attribute on the left is being connected in this direction to the value on the right. For example, our translate here is connected by this line to the corresponding attribute value on the parent constraint node. So now let's take a look. First, we want to focus on the driver object. On our driver object, we see some familiar things like translate, rotate, and scale. They are all connected to some corresponding attributes on the parent constraint. For example, our target translate, target rotate, and target scale. Then the next thing I'd like us to pay close attention to is this attribute called parent matrix. Now, as for what a matrix is, we don't need to worry about that for now. But we can simply think of a matrix as a piece of data that represents an object's translate, rotate, and scale info. Parent matrix. Let's note this. It represents the absolute world position of our driver's parent object. So it's connected to this target parent matrix attribute here. So we know that translate, rotate, and scale are the object's local position to its parent. We add that to our parent object's own world position, which is our parent matrix. When we add all of these together, we get our driver object's world position. Then this world position is used as an input and is connected to the parent constraint node to be calculated. This actually helps explain one of the behaviors we saw earlier, that our driver object, no matter how many parent objects are above it, and no matter which parent object's position changes, it will always affect our driven object. This is what we were talking about. The driver object's world position will affect the constraint object's position. Why does this happen? It's because it's not just translate, rotate, and scale that are part of the calculation. The parent level's position is also part of the calculation. And that's what gives us this result. Because in the end, it's calculating the driver's world position. Okay, next we'll see our driven object here. It also has a few attributes connected to the input column on the left. The one we really need to notice here is this parent inverse matrix. So what does this mean? Again, we don't need to understand the definition of a matrix too deeply. We just need to know that what we're inputting is a world position. But when we output, we are outputting to our translate and rotate. We know these are relative positions relative to the parent. So when converting from a world position to a relative position, we need to use this inverse matrix in the calculation to get a relative position. This parent inverse matrix is the inverse matrix of our parent object's world position. If we use a slightly imperfect example to help us understand what it's kind of like, we've all done multiplication, right? So multiplication, let's say 2 times 3 equals 6. Here, our translate, rotate, scale is like our 2, and the parent object's world position is our 3. That gives us a new value, 6. Okay, so now we have this 6. If we want to go back and find that original relative translate, rotate, scale, what do? If it was multiplication, it would be really simple. We would just do 6 divided by 3 equals 2. But in matrix calculations, there is no division. What does it have? It multiplies by an inverse matrix. So it's one matrix multiplies a second matrix, and that equals a third matrix. When we want to go backwards and solve for the first matrix, we actually use our third matrix multiplied by the inverse of our second matrix. And that gives us our first matrix. So with that information, we can probably figure out that we're getting the driver object's world position factoring in our offset. And from that, we're basically getting the driven object's world position. But what we need is the driven object's translate and rotate info. And this translate and rotate info is relative to the driven's parent object. So we have to factor in its parent inverse matrix, and that's how we get its own relative position to its parent. Now this explains another behavior we found, that no matter how the driven object's parent moves, our driven object itself stays right where it is. Why? Because this parent constraint node first gets an absolute warp position. Then, no matter how our parent level moves, its own warp position's inverse matrix is always part of the calculation. This way, we are constantly getting its new relative position in real time. So no matter what, our driven object stays in place. And finally, let's look at the output of this parent constraint. Here we can see our output. It's outputting its translate and rotate, and connecting them to our translate and rotate over here. This explains the very first thing we noticed about the parent constraint. It doesn't affect our scale at all. And the reason for that is because our parent constraint node itself, when it outputs, it doesn't even consider the scale attribute. So it has no attribute to put in this node, and no attribute to connect to our scale attribute. And that's why our driven object doesn't get scaled at all.